Hello and welcome to Advanced Algorithms. I am so happy to see you here and I'm really looking forward to our journey over the next 12 weeks. Now, this course is a natural follow-up to an algorithms or a data structures course. And in fact, week 1 is all about greedy algorithms, which may sound familiar. You may have seen examples of greedy algorithms in your data structures courses or your algorithms courses. For example, if you have found minimum spanning trees using, say, Prim's algorithm, that would be an example of a greedy algorithm. And so you might find that you're looking at some things that you already know, but I would still encourage you to follow along because this, well, first of all, serves as a refresher. And apart from that, it also sets the stage for our next topic, which is going to be about matroids in the second week. And matroids give us a really powerful abstraction for thinking about greedy algorithms and thinking about them in very general terms. So it really helps to have a few concrete examples to play with as a warm-up. And I hope you'll have fun with the 3 that we have chosen for you. So our first example is going to be a problem called storing files in a tape. Our second problem is going to be a fun scheduling problem. And our third problem is going to be something called stable marriages, which do have a lot of real life applications, as do the other 2 problems as well. Along with these videos, you will also have accompanying course notes, which will sometimes also have simulations of these problems which are interactive. So I really encourage you to check out those as well and play around with them to develop your own intuition for these problems. We also have graded assignments every week, and we also have practice problem sets. I encourage you to go through as much of the material as you can, and please do take advantage of the live sessions to clarify any doubts that you might have. So with all of that administrative backdrop out of the way, let's get started with our first problem this week, which is called storing files in a tape. So here is our setting. We have n files that for some strange reason we want to store on a magnetic tape. Now, chances are that you're perhaps too young to have used magnetic tapes in your day-to-day life. So if you like, you can take a break and go check them out on Wikipedia if you just are curious about what they look like. They were revolutionary technologies back in the day. They were developed in the late 20s, and even as recently as 2014, there were new breakthroughs in how much magnetic tapes could hold. But let's come back to our problem. We have these n files that we want to store on a tape, and what we are given is the lengths of the files. They could all be different lengths. And the question is, how do we want to store them? What do we care about? Well, on magnetic tapes, it turns out that if you want to access a file, you can't just pinpoint at it and get access to it directly. You will have to actually go through all the files that have been stored before it to be able to reach the file that you're actually interested in. Let's get a bit of a visual on what this looks like. So here is this nice gray box, which is going to represent our magnetic tape. And let's say for now we have all of these beautiful files stored on it. The first one has a length of 2, the second one has a length of 5, the third one has a length of 3, and so on. And by the way, if the concept of a magnetic tape is really challenging your imagination, you can imagine that you're trying to pack some books on a vertical bookshelf or something like that. And if you want to access, let's say, the ith book from the top, then that means that you have to actually remove the first I-1 books. And that's going to be, let's say, a heavyweight operation that's proportional to how heavy those books are, which you can think of loosely as being proportional to how wide the books are. So if that helps, you can choose to work with that example instead, but I'm just going to go with a magnetic tape because that's just how the diagrams are here, and it's just easier for me to visualize in the slides. So we have all of these files that are currently on the tape, and let's say we want to access the fourth, it's the fourth file, and it also has length 4. But accessing this file is not just 4 units of cost for going over that file. Like we said earlier, you actually have to access all the files that are before it before you can get to the one you care about. So now that we understand the cost of reading a particular file, let's now think about what is the expected cost of reading a random file. Well, that would be the average of the costs of reading all the individual files. So what we are going to look at is the total cost of reading all the files and then divide that by n. And so this is what our formula for the expected cost looks like, right? And notice that here I'm implicitly assuming that the files are stored in the order in which they are named. So for instance, F1 goes first on the tape and then F2 and so on all the way up to Fn. And recall that F1 has length L1, F2 has length L2 and Fn has length Ln. So now we can expand on this formula a little bit. Notice that the cost of accessing the kth file is simply the sum of the li's starting from 1 to k. So if we were to make that substitution, this is the final expression that we get for the expected cost when the files are stored in the order in which they are given to us. So that naturally motivates the question of whether this is the best cost that we can achieve. Perhaps by reordering the files a little bit, we can make the cost go down further. So to capture this idea of what ordering gives us the best cost, let's talk about the expected cost with respect to a given ordering. So for example, let's say that we are dealing with the files F1 through F6, but we choose to store them on the tape in an order that's different from the default F1, F2, F3, F4, F5, F6. Instead, we store them as shown in this picture. So F5 comes first, then we have F6, then F4, followed by F1, F3, and then F2. And with respect to this ordering, if we try to calculate the expected cost, it's going to be 1 over 6 times the following sum. Well, the cost for accessing F5 is going to be the length of the file F5, which I'm going to say is L5, although we actually know that it's 2, but I'm just going to go with the length notation. So we have L5 as the cost for accessing the file F5, that comes first, followed by L5 plus L6, which is the cost for accessing the second file on the tape, which happens to be the file F6. So the total cost for that is L5 plus L6. Then for F4, we have L5 plus L6 plus L4 and so on. So we're going to have L5 plus L6 plus L4 plus L1 to access the file F1, and similarly for the last two files F3 and F2. For the very last file, it's just going to be the sum of all the 6 file lengths, as you can see. And so that's just going to be the total cost. And like I said, for the expected cost, we're going to have to divide this sum by 6. Now, if you just stare at this example for a few moments, you might realize that this is actually not the best permutation. You can probably play around with the files a little bit and come up with a different permutation that actually gives you a smaller expected cost. One thing that you may have noticed, that the files that come earlier on the tape have their lengths repeated more often in this sum, whereas the files that come later in the tape, their lengths feature less frequently in this sum. So you might have some intuition for supporting the idea that if you want a good ordering, then the files that are longer should be pushed towards the end and the files that are shorter should come first. Now, if you have dealt with greedy algorithms before, then you might remember that intuition can be super tricky when it comes to greedy algorithms. There are greedy strategies that look tantalizingly correct, but they turn out to be often wrong. Not all the time, but you can come up with examples where your algorithm would actually fail miserably. So we want to be really, really sure about the greedy strategies that we propose from the perspective of correctness. So although what I just said seems perfectly reasonable, we want to go a little bit further and actually validate the idea with some sort of a formal argument. So for that, we are going to get back to our notation and setup, and let's talk about the expected cost. Of course, we have seen this expression before, but let's augment it so that we can talk about the expected cost of a particular ordering. So what we had before was the expected cost with respect to the default ordering, which was the boring one, 1, 2, 3, blah, 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 up to n. Now we want to talk about expected cost for a custom ordering, which we are going to denote by pi. So what does pi exactly denote? Well, pi is a permutation of 1 to n, and pi of I denotes the ID of the file that is stored at the ith location on the tape. Well, not literally the ith location. What I mean by this is that it's the ith file from the leftmost end of the tape. So I hope that makes sense. If you go back to the example here, in this permutation, when I talk about pi of 3, that's going to be 4 because that's the ID of the third file stored from the left. So I hope that that notation makes sense. So coming back here, what is the expected cost with respect to pi? Well, now when we expand out the cost function, well, that's going to be with respect to not the sum of Li from 1 to k, but rather the sum of L of pi I from 1 to k, because we want to actually add up the lengths of the files that are actually stored in the first I positions on the tape. And again, by positions, I mean relative order here. So feel free to pause here for a moment and make sure that this expression actually makes sense. All right, so we come back to our main question in this context. What is the order that minimizes the expected cost? And as we have just discussed based on our example from before, the natural strategy seems to prioritize the files that are smaller to go first on the tape. Now, if you want to take this idea and actually turn it into an algorithm, then you would probably say that we should sort the files according to their lengths. You want to sort them, of course, in ascending order so that the shorter files come first and the longer files come later. And you can use your favorite sorting algorithm to get the job done here. And in the subsequent step, you actually push the files in this order on the magnetic tape so that the shorter files come first and the longer files come later. You're welcome to experiment with actually writing code to turn this idea of an algorithm into actually a working program. That would be a fun exercise to do. And also remember that you can play around with the simulations that are available from the course notes to actually get a feel for what's going on. But having said that, our job doesn't end with writing a program, and it doesn't even end with actually putting the program through several tests. You may have a working piece of code that seems to work convincingly on all the scenarios that you can think of, but what we should be doing at this stage, now that we have the intuition and we have a proposed algorithm, is to be proving its correctness. In fact, let me just point out that this is going to be a general pattern that we're going to follow throughout the course. Typically, we will set the stage for a problem and then mess around with a few examples to develop some ideas and build some intuition about possible solutions. And then at some point, we will get to the stage where we can actually propose a concrete algorithm. But that may not actually even be correct, but it's a place to get started. And then we will actually try and attempt to establish that the algorithm is correct, and then one of two things will happen. Either we do have a convincing proof, at which point we should then just move on to analyzing the running time of the algorithm and thinking about if we can do better. But if it turns out that we get stuck in the proof, then we should try and go back to the drawing board, try to understand why the algorithm is not working, develop concrete counterexamples, and use those counterexamples to guide our intuition for perhaps what we should be doing right, how we can fix the algorithm, or just look at different approaches. So it's usually going to be a lot of back and forth between examples and intuition and algorithmic ideas and attempted proofs of correctness, and hopefully we will eventually get to the point where we have a convincing proof of correctness and a solid analysis of the running time and good questions to think about and take back home with us. Now it turns out that since we are starting with this fairly straightforward warm-up example, in this case, spoiler alert, this algorithm actually works, and we should be able to establish that in a few minutes from now. But in general, and especially for greedy algorithms, remember to not skip this step, because no matter how tempting the intuition, it's always possible that without a formal proof, your algorithm may actually have some gaps. And so it's really, really important to go through this step, even if you have done an implementation and even if you have done extensive testing through examples. All right, so with that said, let's actually get to formalizing the main idea behind the correctness proof for this particular algorithm. Again, remember what we are doing is simply sorting the files in increasing order of length, and we claim that this order is the one that minimizes the expected cost. Okay, so now here is a lemma that expresses what we just said, but using notation. So what are we saying here? The claim is that the expected cost is minimized when L of pi of I plus 1 is at least L of pi of I for all I. And when I say for all I here, I've not written it out on the slides yet, but I really mean for all relevant indices I. So the indices I that I care about are the i's between 1 and n minus 1. Notice we don't need to go all the way up to n because that's the last file and there's nothing that comes after it. Now let's break down this expression a little bit. So what is pi of I plus 1? Recall that that's the I plus 1th file from the left end of the tape, and L of pi of I plus 1 is the length of this file. On the other hand, what is L of pi I? Well, that's the length of the file that comes just before it. And what are we demanding here? Well, we are saying that the file that comes after should be at least as long as the file that comes before, and this should be true for all I. In particular, the second file should be at least as long as the first, the third file should be at least as long as the second, and so on. And at the very end, what we are demanding is that the last file should be at least as long as the one that comes just before it. So now if you combine all of these demands that all of these inequalities are making, you'll realize that what we are saying here in this notation is really equivalent to what we were saying before, which is that the expected cost is minimized when the files are stacked up from left to right in non-decreasing order of their file lengths, which is to say, once again, longer files towards the end, shorter files towards the beginning. Okay, so feel free to pause here just to confirm that this notation actually makes sense and it expresses exactly what we wanted to say when we were developing our intuition around the algorithm. And now, well, what remains is to actually prove this lemma, and the way we are going to approach that is using the method of contradiction, which is to say that let's begin by saying suppose not. Suppose this was not true, which means that there is an optimal order which does not respect all of these inequalities, which means that there is an optimal order which violates at least one of the inequalities, and let's pick one of the violated inequalities. Of course, in our heart of hearts, we know that this cannot happen, or at least that's what we are hoping for. So the idea is to make this assumption, run with it, and hopefully arrive at some sort of a contradiction, and then we can come back and say that the assumption has to be false. So we refute the opposite of what we wanted to prove, which means that we have proved what we wanted to prove. So that's the plan, and let's see how it plays out in this particular example. So remember that for the sake of contradiction, we are starting out with an ordering pi, which we claim is optimal, but at the same time has this weird behavior on some pair of consecutive files, where we have the file that comes first being longer than the file that comes just after it. So in particular, we have this file which is the ith file from the left, it's pi of I, and that's a long file, and it's followed by a short one, which is the file at the it's the I plus 1th file from the left. So what we have is that the short file is coming after the long one in pi, and I want you to just stare at this picture and think about how you can go from here to actually finding the contradiction. So what we want to do is actually modify this ordering to find a different ordering whose expected cost is actually smaller than the current ordering. That would basically violate the claimed optimality of pi, and it would give us our desired contradiction. So feel free to take a moment here to try and think about what that modified ordering should look like. It's fairly predictable based on all the intuition that we have built up so far. So feel free to pause here and think for a moment before coming back. All right, so I hope you had a chance to think about that, and let me now tell you about how I plan to modify pi. Let me know in the discussions if you also had the same or a similar idea. So what we want to do is basically stick to pi for the most part, but when it comes to these two files that you can see on your screen, we actually want to swap out their order. So what we want is just restore what is for us the natural order. So we have the shorter file come first and the longer file come after. So we have just swapped the positions of these two files. Now, of course, I'm drawing this by hand, so don't take the lengths too seriously. But basically, you get the idea. We want to just change the order of these two files and observe the impact on the expected cost. So let's think about how the expected cost changes as we move from pi to this new order. You can convince yourself that the cost of accessing all the other files other than these two is basically going to be same in both the orderings. Okay, so we only have to worry about the cost of accessing these two specific files. Now let's think about the shorter file first. As you move from pi to the modified ordering, the cost of accessing the shorter file has actually decreased by quite a bit. Notice that this cost has gone down by L of pi of I, because previously to access the short file you had to actually jump over this large one, whereas in the new order you don't have to do that. So the cost of accessing it is comparable to the cost that was there originally, but it's L of pi I less than before. Similarly, for the long file, we have the opposite experience because it's now positioned after the short one. So the cost of accessing it has actually increased by L of pi of I plus 1, because it now has to jump over, well, you have to now jump over the shorter file to access the longer one. So that's now more expensive than before. Everything else stays the same. So now if you think about the net change of cost, you can observe that because you have reduced more than you have increased, the overall change is actually for the better. The total expected cost has actually gone down as you moved from pi to this modified ordering. But as we suggested before, this is exactly the contradiction that we wanted. So pi is not optimal if there is a competing ordering which does better. So that's our contradiction, and that proves our lemma. Now notice that pi may have had multiple violations of the inequalities that we said should hold, but for this proof to go through, it's enough to hold on to one of them and execute this swap. You don't have to improve the quality of pi all the way up to opt. As long as you can get a better order, you already have your contradiction and you're done. So let's just recap everything that we said. What we are going to do is modify the optimal order, the claimed optimal order, by swapping these two files out, and then we are going to basically compare what happened in the original order and the modified one. And if you look at the before and after picture carefully, you will see that you have had a net improvement in the expected cost, and that's the contradiction that you desired. So that concludes our discussion on the basic file storage problem. In the next part, what we are going to do is talk about the situation where we don't want to deal with an expected cost, but we actually know how frequently each file is being accessed, and we want to minimize the total cost. Give that a thought, and I'll see you back in the next part.